Hi, I'm Andrew Hale. I'm a engineering student at Florida State University. I'm working with Dr. Garcia on the C-band microwave radar system, which is funded by the Gulf of Mexico Research Initiative.
This system was built to mimic synthetic aperture radar satellites by using the same C-band frequency range that they operate. Different media such as water, metal, oil, and oil emulsion can be determined from a change in power received from a target. The goal with this project is to characterize oil and oil emulsion and other material signals. Oil and emulsions have relative permittivities lower than water and dampen ocean surface wave movement. Oil absorbs 80% of the microwave radiation that it receives, while water reflects 80% of it back. The radar system was a result of my undergraduate engineering senior design team's efforts in the previous year at the FAMU FSU College of Engineering. I was the project manager for my team. The design was made from scratch, applying radar communication system principles that we learned from our courses. My group and I determined the components needed to be ordered, assembled the parts, and built the power circuit. The groundwork for making a functioning system was completed by the end of March 2013, and the antenna tower was set up this summer to begin testing. We have another senior design team this year making improvements to the system and making testing easier. There are 7 main components to the system: the antennas, the power circuit, the transmitter block, the receiver block, the mixer, the analog to digital converter, and the computer system. There are 2 antennas in the system. They are at a fixed orientation at a height of about 25 feet above the ground. This is so the antennas are out of the near field range effects. The antennas are directed downward at a tank 14 and 4 inches away from the tower. The tank is 4 by 8 feet and 2 inches deep, which fits most of the beam width of the radar signal. These antennas operate at around 5.4 gigahertz. C-band is a common radar band used by SAR satellites and has lower costs than L and X-band equipment. The signal power used for transmitting is under 2 watts. The polarization used for the transmitting or receiving is a vertical-to-vertical configuration. The antennas have a highly directional beam width at 4.9 degrees, which is good given the small tank area, and this means less environmental noise. I'm going to go ahead and describe some of the elements in the circuit. For the power block, there are 2 primary operating voltages used in most of the components, which are 5 and 12 volts. The circuit receives external power from a wall outlet plug and outputs at 12 volts. A series of 3 voltage regulators create a rail of 5 volts. There are 2 main component types that need power: the voltage-controlled oscillators, or VCOs, and power amplifiers. The transmitter block is comprised of a VCO and amplifier. The signal is boosted before it goes into the LMR cable that leads to the transmitter antenna. The voltage-controlled oscillator generates the C-band signal. It is powered by a 5-volt source and sends the signal over a coaxial connection. As for the amplifiers, there are 4 of them in the design to increase the power of the signal at different points. Most run on 5 volts, as the one shown here, while there's one on the receiver side that operates at 12. The receiver portion of the circuit is a little bit more complex. The incoming signal is amplified twice and fed through a bandpass filter to remove any noise. The bandpass filter only allows frequencies between 4.9 GHz and 6.2 GHz. The signal needs to be amplified so the mixer can operate correctly with the local oscillator side. The local oscillator, or LO, is much like the transmitter block, but its VCO is tuned at a slightly different frequency to mix the signal down to 50 MHz. This allows us to observe the signal on an oscilloscope and also sample the output signal to the computer system. The mixer takes in 2 signals. It takes in the LO signal and the receiver signal, which produces 2 frequencies, one at around 50 MHz, which is what we want to observe, and another higher frequency around 11 GHz, which is a byproduct of mixing. The signal goes through a low-pass filter to remove the higher frequency, and the 50 MHz signal is amplified one last time before being sent through a power splitter. The splitter takes half of the signal power and sends it to the oscilloscope, so that way it can be observed in real time. The other half goes into a power detector, which sends a DC level signal to the analog to digital converter and the data network. The ADC samples the voltage output from the power detector and converts it into a digital value. A script on the Raspberry Pi board collects around 30 voltage samples per second. The data values are written into a data series, which the user operator can see on a data plot on the network server. The Raspberry Pi is set up so that way any user with a computer within the wireless network range of the system's router can connect to it by typing its IP address into their browser. The server on board the Raspberry Pi allows users to set up a test, record and label data, and look back on previous samples. The user specifies the length of time at which they record, then they enter the parameters for testing. Selecting the test button will perform a test and then show the data plot. The Raspberry Pi has its operating system and data stored on a 16 gigabyte SD card, so it is possible to expand or take data off the card. Data can be extracted from the server by searching the database for a set of IDs that can be exported into a .csv file or other formats. Results shown in this graph were taken from multiple tests done back in October. Dr. Garcia and I, as well as a few students from the new senior design team, ran tests to characterize different media. It may be hard to see in this video the different plot points and labels, so I'll describe two of them. The bottom gray line was a test for aluminum covering the bottom of the tank. As expected, much of the signal was reflected away from the receiver antenna. Other media, such as water, had higher returns, as the red line shown at the top indicates a test performed with rudimentary wave generation. We'll be performing more tests this semester to characterize oil and oil emulsion. The new senior design team also has some new ideas for improving the system and testing environment.